Welcome, everybody. This is all going to be about properties of quadrilaterals this afternoon. And although learners meet this in primary school, it all seems quite simple. And I found preparing it that I had to think very hard. I had to do quite a lot of thinking. And this was about defining properties of quadrilaterals. That's all. And so don't, if you're at FET, think, my students have done that in primary school. There's really a lot here. And so we're going to start off with stuff that's very suitable for primary school, but you'll soon see that there is a lot to think about as well. So to introduce myself, I started AIMSEC 20 years ago. Before that, I started a similar website for people to work on problems and share ideas, which was called Enrich in the UK. And I've been working as a teacher at all sorts of different levels for 60 years now.
And I'm Caroline. I founded Bubbly Maths 17 years ago. And my purpose in life is that every child on earth will love learning and enjoy mathematics. And what better way to make that happen than to work with the teachers and the parents so that everyone is successful in this mission. And Marilyn, Barry couldn't help us today because he had a big mission that he had to complete. Marilyn, would you like to introduce yourself quickly as well?
Yes, sure. So my name is Marilyn Buchanan, and I've worked with Tony on and off for the last 20 years.
Longer than that, Marilyn.
Oh, yes, it is longer than that, isn't it, Tony? 23 years, actually. And I'm now retired. I've worked in primary mainly, but also secondary schools and in higher education training teachers. And doing maths education. So I'm delighted to be here. And like Caroline, my desire is every child enjoys mathematics. So welcome, everybody.
So Marilyn has worked for many years in the United States, but she's also from England. And her language, her dialect gives her away. She speaks with a Liverpool accent, which I love because that's where I was born. It's in the north of England. Okay, so we'll go on to talk about, you've seen this before, but no apologies.
So the idea is the work we do, everything we do is based on spiral learning. As Tony said, just because you've done it in primary school doesn't mean that you just drop it. You keep approaching the same subject again and again, and you do it at a different level, and not just at a different level. It's simply that your learners might be understanding it at a different level, even though you're saying the same things to them. So that's how we work, keep addressing the same thing, and we'll go through different levels of similar topics now as we aim at higher attainers. Tony.
Well, what we're going to be talking about, I'm telling you now about the properties, and what we're going to be learning about is properties of quadrilaterals. We're going to be touching on similarity and congruence. We're also going to be mentioning tessellation and symmetry and area. So there's quite a lot there. Now, we'd like you to make comments and suggestions at any time, please. We want this to be interactive. So please put your comments and suggestions on the chat. And when you see the symbol with the little talking heads and the green writing, the green script, it means we want you to answer something. When you see this symbol, you'll see a question in green. Do the activity and answer the question. You might first answer it on your worksheet, but it'll be very good to have some answers on the chat. Now, because of what we were saying about the spiral, we're going to start with number 1 as at the sort of low end of primary here. And this is going to be tessellation of quadrilaterals. And then we're going to come on to, is a square a quadrilateral? Now, think about that question, and we're going to explore that question and do some more work along that theme, squares and rectangles. And then we're going to look at properties of parallelograms and that's a particular sort of quadrilateral, but we've got something to do, some practical work there. Then we're going to be identifying and naming quadrilaterals. And then we're going to look at helices and curvature. Now, you may think of the helix as a spiral, but it's a special sort of spiral. You'll see that. Then we're going to do some card sorting of properties of quadrilaterals and sketching quadrilaterals. And then we're going to look at the minimum number of properties you need to define a shape. And then we're going to look at areas of quadrilaterals. And then we're going to define the properties by diagonals, which is not something we've done under number 7. So we're going to look at a table of properties. This is a sort of summary, really, table of properties and the defining properties, looking at properties of diagonals, whether the diagonals are at right angles, whether they bisect each other, whether the diagonals are the same length, that sort of thing. And then we're going to think about the learning objectives at that stage. We won't be doing that in detail because actually it'll depend very much on the age group you're working with. But perhaps we can think about it when we get there. We might discuss about different age groups and what we might do with different age groups. And then there's the summary where at that point you may like to say that activity I do with grade 5 or that activity I do with grade 9 or whatever occurs to you. So there's the program for today. And so shall we get started?
So the first thing we're going to do is, hopefully you did see the message. We're going to, turn on my camera. Just get a wad of paper. I've got just a wad of used paper. This happens to be A4, but it doesn't have to be A4. And what we're going to do is, with a pair of scissors, you're going to cut a quadrilateral out. I'm not going to draw it first. Simply cut it out. Just use straight lines. I'm going to do that now. I'm going to turn off my camera because I want us all to have a different quadrilateral. So go ahead, get your scissors out, and I'm going to get mine out, and I'm going to turn off the camera so you can't see the quadrilateral that I am making. You can probably hear what I'm doing.
Now, this is if you cut, doesn't have to be absolutely accurate. Don't draw it first, and by cutting through several layers of scrap paper at the same time, you'll make identical, that's congruent quadrilaterals. So that's what Caroline is doing.
I'm doing my best to cut straight lines here. The paper does move, so I'm doing my absolute best to cut identical shapes. They're going to be very close. They're not going to be completely congruent, but they will be close enough. Okay, I have mine cut. Are any of you actually doing this? Because we understand if you can't, because not everybody's in a place where you can, but can you let me know? I've got about 10 here. Melanie wants to know how many. I've got about 10 here. It doesn't have to be loads.
Caroline, why don't you just show us? Well, what we want you to do is try to make a tessellation using your quadrilaterals.
Okay, so it's a jigsaw puzzle. I love jigsaw puzzles.
Yes, if you don't know what a tessellation is, it just means a tiling pattern. Imagine you were tiling your floor with them. No, put them out on the table so they all fit together nice and neatly without overlapping. You have to turn them round. Is it possible?
No, wait a minute.
Caroline's doing her best here.
Have I done that one? Looks like I've not nearly got. Oh, I do have Do you know, I was thinking I must have a 90-degree there, because that looks like a 90-degree angle.
Caroline,
actually,
you're not doing it right.
Caroline, yeah,
are you sure?
Yeah,
Are you sure I'm not doing it right?
I'm absolutely sure.
What am I doing wrong?
Because when you do it, you should get you should get a shape which is you can continue. When you match edges, you should be matching edges of the same length.
Match edges. I've got to match the edges as well.
Yes.
But then aren't I going to have the same angle? No, because I can do it that way. Okay. Match edges. Of course I've got to match edges. Thank you, Tony. When I actually get live on here, I lose the plot. Here we go. Match edges. Is anyone else doing this? It'd be lovely if somebody else is doing it, not just me. Oh, look at that. And oh, that one fits in. Look. The final
Caroline,
one.
Caroline,
Yes.
are we supposed to see your what you're doing? Because we can only see the...
no, right. So
No,
does it
not
need
yet.
spotlighting?
No. Okay.
I'm saying, does mine need to be spotlighted?
I can see
Yes.
it, Caroline. I can see.
You can, but you're presenter.
Oh, now I can. Yes.
I've spotlighted it.
Okay.
So just to go over it again, I've lost the plot. When I go live, my brain switches off sometimes, and every edge has to match. So
Caroline, have you got more than 4, Caroline?
Yes, I do. I'm just reconstructing it because people couldn't see what I did, Tony. So
and I'll put some more in, Caroline.
Yes, I am. So use the same principle again. And let's see. Well, that one doesn't match, so that can't be it. Put that one there. And let's see if that's mine. Is that all right? Am I doing okay?
You can move the light a bit up so that we can see us. It's smaller.
It's as far as it goes, Tony. There is no more.
Oh, okay.
So I've got 2 there. I've managed to get 2 there. I could have done them smaller, but yeah, you don't. There's
so I think we'll move on to the next slide because we've got a picture there. So
I can do a couple here, but yes, you've got a picture on the next slide. Yeah.
Yes. So the question is it possible? And to explain the answer. Now, before we move on, I'd like you to think about how we know. I mean, because these are not done exactly, how do we know that they fit together exactly? The 4 angles around every point make 360 degrees. How do we know that? Let me show you the diagram. Okay. Now that's what Caroline was doing. And what I've done there is to make the 4 angles, to label the 4 angles A, B, C, and D of the quadrilateral. And then I could have labeled them all everywhere, but all I needed to think about was one of the vertices, one of the points where they all meet. And you can see that the 4 angles of a quadrilateral, we know add up to 180 degrees. And by fitting the 4 angles together at a point, the 4 quadrilaterals together at a point, so at that point you've got the 4 different angles of the quadrilateral, you see that they make 360. And so that shows that it must work with every quadrilateral, whatever the shape of the quadrilateral. Now, of course, we often see square tiles. We often see rectangular tiles. We don't very often see tiles in the shape of a quadrilateral, just a general, ordinary sort of quadrilateral, but there is a picture of one. Okay, and that is a nice little activity for quite young children, actually. And then when they do that sort of activity, you say, well, what do you notice about this? And they might notice things like that. They might notice that they do fit together and they could tile the floor with them. They might notice things like the edges match, which we were talking about. They might notice things like the 4 angles around each point come to add up to 180 degrees. They might talk about the fact that if you take this one, can you see my cursor here, and you translate it, you move it horizontally, it goes to that one. And if you move it down, it goes to not the next one, but the next but one. So you've got a reflection in this edge. You might think, say, well, what do you notice about these two? And you might say, well, there's a mirror line here. What do you notice about these two? Well, there's a mirror line here. So you see how many, I think this is absolutely brilliant, because it's a very easy, as Caroline called it, jigsaw puzzle. And what's more, when you say, what do you notice? It's a lovely open question, and you should get lots of answers to that question. And if you don't get any answers about things like mirror lines, you'll say, well, what do you notice about these two shapes? And they might say, well, they're the same shape, but that you might say, well, if you rotate the top one round this point on the middle of this edge, you'll get to the bottom one. Okay, or they might say, if you reflect the one at the top, if you reflect that one in this line, you'll get that one. So that line becomes then a line of symmetry, or a mirror line. There's so many answers there. So
could I just add a point, because as you say, this is a fabulous activity for primary, and for those people who've got younger primary children, you can scaffold this activity by just letting them create the pattern and see what they notice about it, and color in the different shapes, the shapes that match. So like Tony says, that one in the top left-hand corner and the third one down, if they were the same color and the ones that the translation of them were a different color, they'd see a pattern. And then later on, when you get to angles, you can bring this activity back to them, and then look at the angles and look at the reflections or the rotations that are there. So it's an activity that can be ongoing. And you scaffold it in that way.
Yeah, I agree with Marilyn there. And what's more, by asking open questions, it's very, very good for differentiation, because some of the learners, the sort of little bright sparks, will notice things that other people haven't noticed. Well, that's fine, you know. So as you say, you can scaffold it for them, but you stop at a certain point where you think that's enough for this class. But if they're older learners, you'll be probing a bit more deeply and maybe wanting to talk about angles. Okay, but this is still a good activity for secondary, because there's so much in this, and there's a lot about transformations here, as well as the properties of the quadrilaterals. Okay, Caroline.
So here's the question. This is the crux of this whole webinar, this whole session. Is a square a rectangle? So we want you to answer this. We can't see everyone's image. So what we'd like to do is in the chat, write yes or no, or use the reactions. You can just go down the bottom and click on the reactions so we can see the answer to your thoughts. Is a square a rectangle? So I've got, if you're on a computer, the reactions are below, whether you're on a computer or on a phone. Let's see. So we've got yes and a yes. We've got 2 yeses so far. I've got thumbs up, yes. Yes, it's a rectangle. so far we've got 100% answering yes. Now, this is
Well,
a great
don't be influenced. If you really thought before this session that it wasn't, don't let the fact that 5 people have said it is influence you.
Totally agree on that. In fact, I'm going to say it isn't, just to give you a bit of confidence there. If you feel it isn't, I'm going to say they're not the same.
I think because we're mathematicians, we know it is, but I think a lot of people out there in the street would name a rectangle when they saw one, would they might call it an oblong, and they would name a square and they'd say, oh, they're different. They're not the same.
There are a lot of primary school teachers that teach that they are not the same.
Yes.
Okay, so here's the activity. The first thing we want you to write in the comments is what is the same and what is different about the 2 shapes, the square. You see the green square and the green rectangle under activity for all. We want to know what is the same and what is different about those 2 shapes. And once you've answered that, go ahead and move further to the left to see how many rectangles you can see in that diagram. So we want a total number of rectangles. We've asked the question, is a square a rectangle? What is the same, what's different between the square and the rectangle, and how many rectangles can you see in this diagram? We have a few minutes to do this. Go ahead and be thinking about it. And I've done this before, but I'm going to do it again because that'll help us keep track of time as well.
We're spending quite a lot of time on this, and we'll be moving on to other slides and answering these. If we think about this, yes, if you do what Carolina's suggested, just give you a couple of minutes to do that. Also, don't forget the question about the properties of a rectangle, and does a square have all those properties? That's something we're thinking about.
So we've got a square, all sides are equal, rectangle, opposite sides are equal. And I don't know who that is because they've just got the name of their phone. If you can change the name of your phone to your name, that would be great. Zoliswa says all the sides of the square are equal, but only 2 sides are equal for a rectangle. Hassani, there are 6 rectangles and 1 square. That's the answer to how many rectangles. Oh, the clue, it's Tony's clue, not mine. Thank you, Marilyn. The clue is there are more than 10. And there, okay, Melanie, you need to put your money where your mouth is. We want to know how many, not just at least 11. We want to know how many. There's more than 10. Melanie could have it.
We're asked, are you allowed to flip some of them over? Yes, you can turn them around, flip them over. Question is, are they the same shape? And
that was going back to the tessellation, Tony. That was referring to the tessellation when we were doing the previous activity.
Down then, shouldn't I? So Eva says there are 11. Okay.
We've got somebody said 12. Maseko said 12.
I mean both. Somebody says all sides of a square are equal, while 2 sides of a rectangle are equal. Yeah, we'll be coming back to these properties. I'm so impressed that we've got so many answers from you, and no wonder we've asked a lot of questions on this slide. So
and De Sublime says they both add up to 360 degrees. That's usually angle of the square and the rectangle. That's the same. They both add up to 360 degrees.
Both shapes have 4 sides and 4 angles. This is Simpiwe, and both have opposites. Both have opposite sides that are equal. The difference is that the square, all 4 sides are equal, and the rectangle with only 2 sides equal. Okay, we're going to move on. We're not forgetting this. We're going to be doing more about it. Now, this frame is made up of a 4x3 grid. Now, some of you, I think some of you have got up to 13 here. There's more than that. Okay, and what happens when people start shading this in, and they often don't see it, but they've shaded 2 of them, 2 of the templates there in the same way. So just check that you haven't got any that are that you're saying are different, whereas actually they're really the same and in the same positions. Okay, so we wanted you to use this template. You've got to record all possible different rectangles and explain how you know that you've found all the rectangles.
It's hard to find them all. I'm doing my best to be systematic here.
And Caroline, you've seen it done before.
Yeah, I know, and I'm still struggling to spot them all. So it's not an easy activity. Oh, I found another one.
So we'll give you another minute to see if you can find more than 13.
I mean, the reason I'm doing it is to give...
Somebody said 7 rectangles and 3 squares. Well, there are more than that. That's only adding up to 10. There's definitely more than that. Okay, so we're going to move on, and Caroline, you can...
Well, let me tell you that, yeah, I haven't found them. I haven't colored them all in yet. So I know that there's a good chance that others haven't as well. So here's the thing. We're now going to sort the rectangles in the rectangles we've got in boxes 1 to 14 into sets that contain copies of the same rectangle. So we're just simple, same as in 1 by 3 or 2 by 4. These are so I can see a 1 by 2. Tony, can you point out in 10? Let's just look at 10. That's a 1 by 2. So I'm going to put
10 is a 1 by 2.
And I'm going to write in the chat.
In the same set, you would have 5. 5 is in the same set as 10. And 8 is in that same set as well. And 12 is in that same set. So that set has got 4 elements: 5, 8, 10, and 12. That's 1 by 2. Okay. Now, what else?
This is how you write it. As I've put it in the chat now, that's a 1 by 2.
Okay.
That's the
no. That's not right, Caroline. That says that 1 and 2 are in the same set, which they're not.
Oh, what am I doing? Yes, ignore me.
So that's wrong, Caroline.
I'm doing it again. I'm showing you what's wrong. So I'm giving you the opportunity to do it.
They're 1 by 2, right? So they're 1 by 2, 1 by 2. And then it's in this set, you've got numbers 5, right. 8.
Are you typing it in, Tony?
Yes, I'm typing it in now.
Okay, right.
10 and 12. And when you list members of a set, you always do it with square, with curly brackets. So they're 1 by 2 rectangles, and they're on the picture, they're numbers 5, 8, 10, and 12. I hope that's clear. So we'll just give you a minute to write down the other sets. So the next set to write down would be 1 by 3, which includes number 1. And what else goes with number 1? Is there another 1 by 3 that you can see?
Oh, no. Yeah, 9.
And then there's one, then there's another set which has got 1 by 4 in it, and I don't think you're going to find anything else that's 1 by 4.
One.
Because the reason is that there's not 4 squares across this template, so you can't put it horizontally anywhere.
Yeah, the whole grid is 4 by 3 or 3 by 4. And remember the 1 by 1.
Yes, and there's no top to bottom for you know, a rectangle with there's 4 by 1, 1 by 4. Then the next one is 1 by 1, and there seems to be only one of those. We've already talked about 4 and 5. The next one is number 6, which is 2 by 2. And there's only, oh, there's 11 in that one. Number 7 is 2 by 4.
2 by 4.
Yes, and that's the only one of those. Number 9 is 2 by 3. It's the only one of those. We've had 11, went with 6. And we've had 12, which was 1 by 2, went with 10 and 5 and so on. 13 was 3 by 3, and it's on its own. And 14 is 3 by 4. Okay. So the next question is another question here. It's about language. What do we call the same? There's a mathematical word for that. It's a shape with all corresponding angles and all corresponding lengths equal. I'm sure you know that. You can write it in the chat if you want to. What's the mathematical word for that? If all the edges are the same length or corresponding pairs of edges are the same length. I don't mean they're all edges are the same length. That's nonsense. Corresponding pairs of edges are the same length and corresponding angles are the same. They're the same shape. We have a mathematical word for that, which is congruent.
Yeah, we had a few people answer with congruent.
Well done. Talu, Maseko, and Sinahanya. Yeah, lots of people have said that. So now the next question is.
We're now going to turn it around. We're going to ask what is a similar. Spot the rectangles in the box, and we're now looking for the meaning of the word similar.
Yeah, you want to.
And then just want to be super clear on this. It is different to congruent.
So you need to list here. Well, first of all, say what you think similar means. It's not the same as congruent. Say what you think it means. It is a mathematical word, as you know.
Equilateral means all the edges are the same length. Equal laterals.
Yes.
Equal, as in the same, lateral means edge or side. So equilateral means all the edges are the same length.
Now, De Sublime has said that a similar it's similar is the shapes, same shape with different size. So the angles are going to be the same, but it's a different size. And in fact, this is something we meet all the time when we pick up our phones, that we have got two similar shapes. You know, I see an image of something on my phone, small, and it's probably much bigger than that in reality. Okay, I'm looking at pictures of all of your pretty faces, your handsome faces, and they're much smaller than your real faces because I'm looking at pictures on my screen. Okay,
it's a scale model.
It's a scale model. Yes,
it may be a larger scale or smaller scale, but unless it's a one-to-one scale, it's similar, not congruent.
So they have all pairs of corresponding angles equal and corresponding lengths in the same ratio are called similar.
Okay, look, Zoliswa has said a good one. Similar means different sizes, but same shape or figure.
Yes, that's great. Well, one's an enlargement of the other. We haven't said that
Well,
yet.
it says different sizes.
Yes.
Different sizes, same shape.
Yeah, but enlargement is a mathematical word which we might have used there. And there's a lot of sort of mathematics where we're talking about similar, where actually we've really got one. We should, if we bear in mind that one is an enlargement of the other, all the maths we know about enlargement applies when things are similar. But we also often want to put them in an orientation, turn them round, so we can see that enlargement with, if it were rays, like the rays of light projecting something on a screen, you could join corresponding points. So we're going to move on to the next slide. Now, this is, as we, what we want you to do is to say which, what we asked you to do was to sort the rectangles into shapes which are congruent, and we mentioned what they were, but there is the list. All right, so for example, 3 wasn't congruent to anything else there, but 5, 8, 10, and 12 were congruent to each other, and we talked about that already. And we wanted to do something similar to that in terms of listing sets, but now they're not necessarily congruent, but are they similar? So can you pick out pairs, or maybe even 3 in some cases, perhaps not, in there, 3 rectangles or 2 rectangles which are similar? And put those on the chat if you can. Pairs of similar rectangles from that diagram.
Melanie's made a list of all the squares.
Brilliant.
On there.
Brilliant, Melanie. Yes, absolutely. Any more?
At the moment, that's the, now this is where you do, 1 and 2 are similar. So Liswa, 1 and 2. Then the proportions are not the same. Snez said they're the same shape with proportional size. So the proportion between the edge lengths has to be the same. And 1 and 2 is a 1 by 3, 2 is a 1 by 4. They're not proportional. One is not an enlargement or the other. So keep looking. That there might not be another equivalent, because for there to be an enlargement of number 1, it would have to be if it was, say, doubled, it would have to be 2 by 6 or something that's ever so slightly bigger. It won't be a 1 by anything.
So if you see here, you can put all these 3, 6, 11, and 13 into one set. That would have been correct, as Melanie did it on the chat. They are all similar. And 5 and 7 and 8 are all similar. Can you see 5 and 7? 5 is 1 by 2 and 7 is 2 by 4. And of course, 8 is the same as 5, so it's also similar to 7. And then
okay,
10.
So yeah, Yega has said 8 and 10, they are congruent, and 1 and 4 are congruent. So we've got congruent ones there, yeah.
Yes, well, the congruent ones are above on the screen. You see them listed in sets above, and the ones that are similar are written below. So 10 and 12 are.
I just want to say, for the people that aren't getting it right the first time, it's like myself. Sometimes it's just that you're not thinking because you're on the spot. And other times, if you're learning something new, which I have learned a lot of new things working with Tony, this is where you need to be to keep this fresh in your mind and make sure that you're conveying the right message to the learners. Thank you.
Yeah, so if you shrink 7 down, you could shrink it down to 5, you could shrink it down to 8, and you could shrink it down to 12 by halving everything. So it's a 2 by 4. If you made it a 1 by 2, that is 5, 8, and 12. Okay, so let's move on. And now I would like you to think about enlargement here, and also the scale factors of the enlargements. So now we're thinking about similarity again, and pairs like 3 and 11.
And so now we're looking at, you can actually, with this these diagrams, it's quite easy to work out the scale factor. So between 3 and 11, what has happened to the length of each edge? The 3's are 1 by 1, 11's are 2 by 2. The shape is the same, they are similar. What is the scale factor?
Not 11.
Maseko says the scale factor is 2. We've got one answer that says the scale factor is 2. Now, in your classrooms, you can take answers, but we're not going to say who's right and who's wrong or whatever. But we want to hear all the answers, and then we can help. Nan has their hand up. Did you want to say something? Is this Did you want your hand up? Did you want to say something? You can unmute yourself if you do. Or just put a comment in the
Yeah.
I'm just looking for the name I know you by. I've got about 3 people from my tutor group here.
Nan, you've got your hand up, and we'd love you to speak if you want to speak, but you need to unmute yourself. Okay, well, we'll go on then.
It's Namita. You can speak if you want to, Namita. We've got quite a few people that say that scale factor is 2. They seem to be quite confident that the scale factor is 2.
Great, that's great. So the next 3 to 11 is 2, but what about 11 to 3? That's the other way around. That's halving it, halving the lengths of the edges, 11 to 3.
And then we've got another example, let's say from 5 to 7. That's a different shape. We've got a 1 by 2. And what's the 7? 2 by 4. Again, what's the scale factor? We can enlarge it, as in make it bigger, but we can also an enlargement that's less than 1 to make it smaller.
And this use of the word enlargement in mathematics is different from how most people think that if you enlarge something, you make it bigger. But in mathematics, enlargement and similarity mean the same thing. So you have a similar shape, and it can be bigger or smaller.
So you're enlarging it by a factor that's less than 1.
Yes, yes. And I think that's quite confusing for learners when they first hear that, because it's not, and there's quite a lot of words where there will be people here from the mathematical communication course, and there we're investigating how we use words in mathematics more precisely or in a different way to work to the way we use those same words in everyday talk, and that's making the mathematics, it makes for difficulties, particularly if English isn't language of instruction, isn't your home language.
And certainly for primary, I would not get into the fact that an enlargement can be to reduce the size, because it's, as you say, Tony, particularly if you're operating in 2 languages, it would be way too confusing. So you're better off at that point sticking with to make something larger, to enlarge it. So
keep the same shape. So keep the angles the same. It's keeping the angles the same. That's while you change the lengths, and all the lengths are changed in the same way, according to the same rule. Yes. I think you can see that there's quite a lot to talk about here. And we're not repeating ourselves. We're actually looking at different aspects of this same question here. Now, describe the transformations that move one congruent shape to another. So, for example, I've put some dots in these diagrams. If you rotate number 1 by the point and this point here, then, and you rotate it 90 degrees clockwise, then it goes into position 4. Which is, now, what would go, which pairs could you go from one to the other when you translate 1 unit up? See what would go from one to another if you translated it 1 unit up.
Just give us the number. Of the 2 boxes, the 2.
You've also got from
Maseko says 6 to 11 is 1 unit up.
I think that's 2 units up.
Oh, right. You're being, I saw it the same way as Maseko. I see what you're saying.
An edge length
up.
Yeah, but absolutely right.
Its whole shape has moved to above itself. But it isn't 1 unit, it's 2 units.
That's 2 units in this 3x4 rectangle. But also, if you see on number 4, I've put a dot, and that rotates to, where does it rotate?
To number 1.
Oh yes, that rotates to number 1. 1 rotates to 4 if you rotate about that dot. And if you look at number 8, okay, you can rotate about that dot as well. And what do you get number 10. There's so much to spot here.
As Tony pointed out, those are rotating about one of the vertices of the shapes. You can rotate others of the shapes with a different axis of rotation that isn't one of the vertices of
and if you're doing our mathematical thinking course at the moment, you'll be, I think that's the one where they're concentrating a lot on this is for the lower secondary group, are concentrating on constructions, ruler and pencil constructions. and how you rule and compass constructions. And to find the center, you join corresponding points, and then you do the perpendicular bisectors of those joins, and that will give you the center of rotation. So we're not going into that complication now, but that is, so if we now look at,
we've had also 5 to 8, so that is literally 1 unit up. 5, if you translate that to 8, that is 1 unit. It has moved.
yes, so there we go. 5 to 8 is 1 unit up. I haven't put in this list 2 units up, but 2 units up is 6 to 11, isn't it? Now, rotation of 90 degrees and a rotation of 90 degrees and a translation. 5 goes to 10 by rotation of 90 degrees and a translation. Actually, by the method of construction that I just described, that you could find the center of rotation, but we're not going to do that. 5 also goes to 12, again, by rotation of 90 degrees combined with a translation. So we're talking a lot about transformations here, and this is something that's covered and discussed and worked on at lower secondary. So it's not really primary work, but it begins to come into primary. How could you turn that one round? How could you rotate it? How could you reflect it or how could you move it along a straight line to get the other shape? Those are the transformations we're talking about. And then translation or reflection, 10 will go to 12. If we look at 10 and 12, they could be either by reflection in this line that I'm showing you with my cursor, or by rotation about the midpoint of that line. And similarly, 6 and 11 will go to one to the other by reflection in this horizontal edge here, or rotation about the midpoint of that edge. So when you start to ask open questions about this, you'll see it's a very rich activity, because there's so many ideas that you can bring out or not bring out, if you haven't got the time, or if they're younger learners or older learners and you don't want to spend the time, but it's there if you want to spend the time.
Before you pass on, Tony, could I just chip in again with a plug-in here for the primary? And again, to scaffold for down the road, if you take the shapes that you have cut out and you want to show students how they can rotate around a point, then if you have a drawing pin or a thumbtack, you can put it in one of the edges, and as they move it round, they draw around the shape. Now, what they'll come up with is a very interesting pattern that they like, but it also shows, it demonstrates about rotations, or they can turn the shape and draw around it, much like we did with the tessellations, where they keep moving it along a line, so that it's, when you introduce it later to return to this theme, they've got prior knowledge that they can tie it to. So that's how, we could introduce this at the younger age group.
That's lovely. And another way Caroline's just going to show us, and if you look at this slide, is to use tracing paper. Yes. So to trace your shape, and then move, and then you've got the original and you've got the tracing of it, and you can move the tracing paper around to show what's equal to what, and what you can move from one edge to another edge, and make them show that they're corresponding or equal in length. Okay, Caroline is going to do this. So we're looking at properties now only of parallelograms. And Caroline, if you look at the her visualizer, I think it's spotlighted. Can you see it, Melanie? or maybe your presenter, and we hope you can see this.
Yes,
Melanie, ask Melanie.
You can.
Melanie, can you see it? Can you see what Caroline's doing? So I'll describe what she's doing. I hope everybody.
Yes, I can.
Good. So what? We've got a Melanie who's helping us and a Marilyn who's helping.
Oh, but you were misnaming me.
No, not at all, Marilyn.
So with as you see on the slide, the rulers are different widths. So we don't get a rhombus. We actually get a parallelogram by drawing on just going along the edges of the rulers, as Caroline is doing now. And you see beautifully, she has got a parallelogram there. And now she gets a piece of kitchen baking paper and uses that as tracing paper. And she just draws those lines on the tracing paper. Then she's going to be able to move the tracing paper around in different ways to discover which lengths in a parallelogram are equal and which angles are equal.
And this is just paper I got from the kitchen. It's hard to get tracing paper these days. So this is just the paper that you use for cooking. Whoopsie. Paper that you use for cooking. I could use the other ruler again. That might make more sense.
As a little tip, as a teacher, when I ask children to construct something accurately, right, so that they would all be doing it the same shape and same size, I would have a copy on tracing paper and walk around the classroom and put it on top of theirs to see whether theirs was right or not. It was very much quicker with me holding a little bit of tracing paper with the, how it ought to be on the tracing paper. It was very much quicker than stopping to look at each one and see, is that right or is it not right?
That's a good idea, Tony.
Yeah, and
you couldn't do it with this activity though, because it's going to be different.
Oh yes, exactly. And the point about this activity is, I was just talking about tracing paper. The point about this activity is, it is beautiful, isn't it? Because what it shows is the different, you see all sorts of different mathematics in it just by moving the tracing paper around. And it's so simple.
So we can see that that angle is the same as that angle. Know that. What about these two here? Let's turn it round and see if they are the same. And hey presto, that angle is the same as that one. Oh my goodness. That one is the same. So those four are all the same. Now what else can we do? I'll just turn this light on, might help a bit. I wonder about these two angles. Is this the same as that? Let's move it over there. And we can see it. They can literally learn all of the properties of parallel lines and opposite angles for themselves using tracing paper.
And this is a great activity for the class because you ask the children to work in pairs and do this, or even to work individually and then discuss it in pairs. And they might do the 1, 2, 4. They might then discuss it in groups of 4. And then as a whole class, get them to tell you what they've discovered. The question here is what can you discover about parallelograms? And when you discuss it as a whole class, different pairs or different groups of learners will have noticed and discovered different properties. This is an activity which you can also look at, sort the quadrilaterals into sets and name them.
The squares are simple. Spot 1, 6. I'm just actually spotting them now. 1, 2, 3, 4. Oh, this goes across. 1, 6. I like the fact that one of the squares is at an angle. 8, and more than one, and 11. Different sizes. So there's some of them are similar. Rectangles, again, 7, 13, 14, and 16. Now we have kites. So we have to be sure that they have symmetry. So that's 3, 4, and 5. Trapezia, with 2 parallel lines, 2, 9, 12, and 15. And then we have one that doesn't fit into any of these categories, which is a quadrilateral, and that would be a perfectly legitimate name for it. This one does actually have symmetry, but you can call it an arrowhead, but it's not a formal name for it. It's a non-convex quadrilateral if you were looking for an official name for it.
And so one of its angles is more than 180 degrees. That makes it non-convex.
One of its internal angles, yeah.
And now we come on to helices. Now, this I made with a toilet roll core, okay, the cardboard from the inside when you finish using a toilet roll. And I drew 2 sets of parallel lines on this before I did anything else. I drew them straight along the cylinder and at right angles. So the green lines are vertical there, and the blue lines are horizontal. So I made a grid. It wasn't perfect, but I had to do it on the edge of the cylinder, this core. And then I drew with a pink marker a line where this was glued together. So actually you can see my keyboard behind that picture on the left there. That's sitting on my keyboard, okay, or just in front of my keyboard on the pad. And then I then pulled it apart along the pink line and opened it out. And goodness me, Caroline's doing another one, which was made the same way, but this time, instead of drawing along where the toilet roll was originally, the core was originally made, this is drawing another helix on it. And Caroline just flattened that out. And that is, look, it's also a quadrilateral, but it's so long and thin, she can't get it all on her, under her light at the same time.
But it is a parallelogram.
Yes, okay.
That's a nice investigation you can do with your learners, that they can all follow a different line. But you do have to make sure that it is a proper line. Use good ways of making, I use basically tape measure.
The other question is, what's the curvature of this helix, which is shown in a pink line on the diagrams? What's its curvature? Now, curvature isn't something that you learn about in school, really. It's something for university maths, actually. But you could ask the question, is it curved? There's the question. Is it curved? Well, it certainly looks curved when it's actually on the edge of the cylinder. But I could be showing you a can of tomatoes or something with a label on it. Now, you're all used to the idea of bottles and cans having labels on them. And when if that label isn't actually stuck to the surface, it's just tightly wrapped round. And if you then cut it carefully and open it out, it makes a rectangle. So though it looks to be curved around the cylinder, actually it can be flat. So in mathematics, we say that has got 0 curvature.
You can also do the same again with toilet roll, simply cut it in a perpendicular line from the top circle to the bottom circle and open it out, same thing.
One of my green lines there, yes. And so the answer is that pink line, the spiral or helix, the helix is the correct mathematical term. There are other sorts of spirals, you see. You don't have to have this property, the properties you see here, for all spirals. It isn't curved at all in mathematical terms. It's got 0 curvature. okay, because it flattens out into a straight line, which I think is quite lovely. Yes. So the spiral helix has no curvature at all. It isn't curved, it's a straight line. So that is a nice little mathematical fact. And as an example, in real life, we've all met spiral staircases, and then there's lots of other spirals in nature that we see in shells and in the heads of flowers, the arrangement of the seeds on the heads of the flowers, and there are other spirals. But this is a helix, which is rather nice, isn't it?
So this is an activity for you now. The question is, so you only have to type in, well, just first of all, name the quadrilaterals that you see. So we've got set cards of letter A, B, and C. They are 3 different quadrilaterals. We want you to name them according to the description, sketch the quadrilaterals, and then decide on the minimum number of properties that you need to define it. So are you going to need A1, A2, A3, A4, and A5, or can you, what is the minimum amount of those descriptions, and make a list of the,
so we're going
the descriptions you need. Go on.
We're going to give you some time to do this. So you should all, even if you haven't got the worksheet, you can all sketch the shape that is described by all those cards under A. You can all sketch it, and you can decide if you need all the properties there in order to be sure it's the shape you've named. And then do the same for B, and then do the same for C. So, and you can write, well, perhaps it would be better if you didn't write the answers just yet, because we want everybody to have a go without looking at other people's answers.
And I'm doing the activity so that we've got an idea of how long it's going to take you. Let us know when you've got all 3 done.
Three shapes, 3 drawings, and then for each one, decide on the minimal number of properties required to define this particular shape. Quadrilateral, they're all quadrilaterals. And then when you've done it, just put your name and done on the chat so we know you've done it.
I've drawn the three shapes, Tony. So I haven't spent the time figuring out what the minimum requirements are, but
I'm going to give everybody just a few more seconds to decide on minimum number of properties, and then we'll discuss it all together. So what we mean by that question is, because you've got some dimensions, they're not need to define. In fact, they don't define all squares. They just define the one you've sketched. But if you wanted something to define all squares, what would you need in A? And so we're going to move on, but before I do, if you look at this little picture, this is actually a class. We do this often as a class activity. We give learners a big sheet of paper, one of these flip chart papers, if you've got them, and you ask them to divide it into 6 areas, you know, a line across and 3 lines the other way, and then they've got 6 boxes, and they do each, we've got 6 of these sets of cards. They've got 6 of these to do. We're just looking at 3 of them for now, and they put one in, they do this one in each box, and that makes a poster of it. Okay, now here's the drawings. So A describes squares, and there are all the properties marked on the equal angles and the equal edge lengths, and the fact that it's 5 centimeters. Okay, and the second,
just to clarify something, you did say, Tony, that you need to know what the properties were that don't include the dimensions, where the dimensions aren't necessary, the generic shape. So
yeah,
so that your list of A2 and A3 and A4 include, just to say, it includes the dimensions, so it can be even simpler than A2, A3 and A4.
Yes, and if you have just A3 and no, if you have the diagonals of shape bisect each other, A1 and A3, for example, we're going to come on to this later and discuss it in greater length, but A1 and A3 are enough. Okay, so going on to the rectangle, A1 and A3 would describe all squares, and then when you want the dimensions in it, you can look at A2, A3, and also you look at A4 as well. The rectangle, now that's all you need to describe the rectangle as we've drawn it with those dimensions, is B1, B3, and B5. Is that right? Yes, so we've got the 4 centimeters and the 6 centimeters give the dimensions, and B3, it has 4 equal angles, and so they must all be 90 degrees because the angles must add up to 90 as it's a quadrilateral.
And if you didn't have the dimensions, you've got a combination of B2, B3, and B4, don't you? If all the angles are equal, then there's only one angle that they can be. No, 4 equal angles, there's only one angle they can be.
So we're going to look at this. I've got a table of properties later, and we're going to look at this again. But what's I think you might be a little bit surprised, but the minimal of these properties here for a rectangle, the diagonals have to bisect each other, and it's also got to have 4 equal angles, because the diagonals, if they bisected each other, it could even be a kite. But then if, because that, no, it's not true of a rhombus, it could be a rhombus. But the best, if it's got 4 equal angles, it makes it either a square or a rectangle. But for the rectangle, they don't bisect each other at right angles, whereas they do for a square. Talking about the diagonals there. Now the parallelogram, for the dimensions, we need C2, C3, and C4. But C5, opposite sides of the shape are parallel. That is actually enough on its own if you don't need the dimensions. C5 would be enough on its own.
Well, that doesn't tell you it's not a square or a rectangle, though.
No, but it tells you it's a parallelogram, and they're parallelograms too.
That's true. We had that discussion earlier, didn't we?
Well, yes. Well, I mean, just as it's true that a square is a rectangle, also a square is a square and a parallelogram do both. I mean, all you need for a parallelogram is the opposite sides of the shape. And so that is true of a square. So a square is a parallelogram, but it's a special one. And for a rectangle, again, the opposite edges are parallel. In this case, they're not equal, but they're parallel. And that makes a rectangle into a parallelogram as well.
So it's a nice point of discussion. But if we wanted a learner to actually draw a parallelogram where the edges were not the same length, then it's just a matter of working out what is without giving dimensions.
They wouldn't be able to do it. They wouldn't be able to do a parallelogram that didn't have equal opposite edges equal.
Yeah, no. Yeah, I'm just saying that you could, if you actually wanted from the clues to actually draw a parallelogram where the angles were not 90 degrees and the opposite edges were equal but not the same as each other, then what would the minimum you need? It's just part of the discussion you could have about it. That's all.
Okay, so now we're going to do the same thing here, but with 3 more shapes.
Right, I'm going to draw them again so that you know an idea of time.
Sketch them and decide on the minimal number of properties required to define the quadrilateral. Moses has put down D1 to D4 describe a rhombus. D1 to D5 describe a rhombus, and D5 gives the edge length. And this is what Moses has put down. You may not agree, but this is what Moses has put down. He's got E1 to E5 describe a kite, and then he's not put down anything for F. No, so Liswa has said F1 to S5 is a trapezium. And that is right. We call it a trapezium in South Africa. We call it a trapezium wherever we use English. Okay.
Yes, and they call it a trapezoid in the US.
Yes, and that can create a bit of a problem sometimes. Yeah. Yes. Nadedwa says it's a trapezium. Well done, well done. So let's look at the diagrams here. There we go. There's the words and the diagrams again. So D is a rhombus, and to get this rhombus of these dimensions, you need all 4 of the sides equal, and you need the opposite sides of the shape are parallel, and the shape has at least one side that's 7 centimeters long. And that, I think, is enough. It's all 4 sides are equal, means it's either a square or a rhombus, okay? And
but you know it's not a square because it has at least 170-degree angle.
Exactly, so it's not a square, and the shape has at least one side that is 7 centimeters long, and that gives you the edge length of that shape. Notice I'm using the word edge and this word side here, and we use them to mean the same thing, but side is often used for a different with a different slightly different meaning. Use, you know, my left side and my right side is the whole of one side or the whole of the other side, okay? Whereas the edge is very definitely just what's on the edge, okay?
Yeah, and with it, especially like a 3D, let's say, just take a cube.
Yeah,
people can talk about the size of a cube and size of 3-dimensional, but we don't know if you're talking about the, let's keep it a cube, if you're talking about the square face or the actual edge of a cube, for example. So
that's why I try to use the word edge rather than side, but I'm so used to using side, I sometimes use that inadvertently. I'm trying to use the word edge. Now, all those E cards describe a kite, and it's, of course, it's slightly different from it is different, significantly different from a rhombus, and so to get the dimensions here, you need E1 and E2 and E5.
Yeah.
And then the diagonals of the shape intersect each other at right angles. Do we actually need that here?
The question is, do you well, let's put it this way, it helped me make sure I was I don't know if it's absolutely essential,
yeah,
but if you don't have the dimensions, then I'm not.
That would describe it completely, actually.
Yeah,
The dimensions. Yes.
Yeah.
It would describe it, and we'll talk about more about that. I've got another picture where that's shown quite nicely. And then in the last one, it's a trapezium. It actually happens to be isosceles, and that isn't. We've got more than one type of trapezium. All a trapezium has to be is two opposite edges parallel. But this one is isosceles. It's a bit like a cut-off or a truncated isosceles triangle. So there's two angles, two adjacent angles. There's a 60 and 220 there. 60-degree angle is given in F3. But you actually need, in order to describe this with all its properties, you actually need, I think you need F1, F2, F3, F4, and F5. Okay, so we'll move on, and Caroline's going to talk about about area.
Right, yes. So we'll start with the parallelogram on the left. We're going to look at the area of all the 6 shapes we've just looked at, and we're going to go back to one that appeared earlier on. So just look at the parallelogram. This is a great way of both understanding it for yourself and to help the learners understand how you work out the area of a parallelogram. So if you literally splice off that triangle to the left and place it in the place to the right, you've got a rectangle, the area being base times height. Super simple. If you're not given the height, which very often a lot of the questions for certainly senior phase and middle school are given, you're given the height. It's just a matter of remembering it. But if you can get the learners to visualize that, okay, let's just turn it into a rectangle, and then we can, rather than having to remember, we can work out the height. It's just a nice way to do it, and it gives you more agility with geometry as well when you're juggling shapes around to make them, to help the area. Now, the area for the square, super simple, base times height, area of the rectangle, again, length times height. Now the parallelogram is a little bit, you do need your trigonometry there. So you've got, because we haven't been given the height in this particular instance, you've just got to do, it is still base times height. We can see that from the image on the left, but if we're not given the height, then you just have to use trigonometry to work out the height. And once your learners have the trigonometry, it's a simple solution if they understand the image in that beige box. Going on to the rhombus, again, you need the trigonometry in order to solve it, but the answer is it's half the product of the length of the diagonals. And if you translate, we haven't got an interpretation of that to make it easy to visualize, but that is along the same lines. And now if we just look at the
Caroline, could I just,
go ahead.
There is a way to visualize it.
Okay, go ahead, Tony.
Imagine a rectangle around this. Imagine a rectangle being drawn with horizontal and vertical lines to sort of frame it. Then I think you can see which would have the same width and the same height, but would be a rectangle, okay? And then I think you might imagine, we could do this with folding paper, Caroline, that this is half the area of that rectangle, okay? So the lengths of the diagonals are the lengths of the edges of the rectangle I'm talking about, and this is half of them because it's well, if you folded the corners of the rectangle down to the middle, then they'd all you get 4 triangles.
Yeah. Okay, so yeah, it's a great way to manipulate it to work that out. The next one, you just need Pythagoras. You've got right angles in the center because it's a kite, and you just need Pythagoras to work out the lengths that you don't have now. So the area, again, if you draw, it's the same kind of thing. You draw a rectangle around the outside of it, and so then you can see that it's made up of, the rectangle has twice the area of the area underneath. So all you need to do is work out the length, which is 2√2 plus √21, the height, which is 2 centimeters plus 2 centimeters. 2√3, sorry, couldn't see that, sorry. I'm looking at the piece of paper instead of on the screen, and because I'm drawing, oh, you've got it there, you've drawn it there, how wonderful, it wasn't there before, lovely, fantastic. And so, and then it's half of that, it's simply half of 4 times 2√3 plus √21, and making those rectangles is so powerful. Finally, the trapezium is the sum of the lengths of the parallel sides times the distance between them. Again, make it into rectangles and triangles to take the knowledge that they've got to be able to work out, discover why these aren't mystical formulas that have just appeared and someone said, oh, let's make it this. They can figure out for themselves why the area of a trapezium is the sum of the lengths of the parallel sides times the distance between them. I like to look at it as you've got half the base times the height of two triangles, basically, half the base times the height times 2, which is why.
So that's really nice. And that 5√3 there comes from, you might say it came from Pythagoras' theorem, but you shouldn't have to use Pythagoras' theorem, because the 30, 60, 90 triangle is a standard triangle, and you should know that, and it helps your learners if they know that the ratios of the edges, and therefore the sine and the cosine, are in the ratio. We'll know the sine and the cosine if we know the ratios of the edges are 1 to 2 to √3, and that's everybody doing maths and sort of middle school should recognize, once they do trigonometry anyway, they shouldn't need to use trigonometry for that. It should be something they recognize immediately. It's half an equilateral triangle, by the way. That's what it is. Okay, so now I've got a really nice table here, and what it shows you is defining properties and other properties. So if we look, and we're looking again at the square, rectangle, rhombus, kite, parallelogram, and the isosceles trapezium, but we've also got the trapezium below, which is not isosceles, it's just a general trapezium, which we didn't have on the previous set with the other cards. Now, if we look at the diagonals, if we focus on the diagonals, I think they will actually be enough to tell us everything we need to know to make sure it's a square. Okay. Now, if the diagonals are equal and they bisect each other at right angles, that's not what I want to do. Sorry about that. Why did that come up? There we go. There we go. I will need to see where there it is. There we go. If the diagonals are equal and they bisect each other at right angles, as you see there, then it has to be a square. And that's all we need to know in order to get a square. If the diagonals are equal and bisect each other, but not at right angles, not necessarily at right angles, in this case, we want something different from a square. So what makes it a rectangle is the diagonals bisect each other. That makes it a rectangle, but not at right angles. And there you can see that, yes, because a square has the properties of a rectangle, a square is a rectangle. Now, if we look at the next one, these diagonals bisect each other at right angles, but they're not necessarily equal, and that's the rhombus. Okay, these diagonals do bisect each other at right angles, like the square, but then they're not equal. So this is not a square, it's a rhombus. But we can see that a square is actually a rhombus because it has, to make it a square, to make it actually something we'll name a square, and not a special case of a rhombus, the diagonals of this rhombus would have to they would have to be equal, and the ones in the rhombus are not. Now, what do you think about the kite before I click on that square, and you can see what happens with a kite? One diagonal bisects the other at right angles. There you go. But the only one that bisects the other. They don't both bisect each other, and that makes it a kite. And in the kite, you see, you've got two isosceles triangles go together to make up the kite, don't they? And the blue edges are equal and the red edges are equal. Whereas in the rhombus, all 4 edges are equal. And in the rhombus, opposite angle, both pairs of opposite angles are equal, but in the kite, only 1 pair of opposite angles are equal. I think you might find this, this particular slide really useful with your learners. And it's something that at FET, when they come into what is grade 10 in South Africa, if they did this sorting with those sets A, B, C, D, E, and then they fill this in, this would be really useful for them. Now here, if the diagonals just bisect each other, but not at right angles, you get a parallelogram every time. Now, 2 pairs of adjacent angles equal, that actually gives you the isosceles trapezium. As I mentioned earlier, it's as if you had a isosceles triangle and you cut it into you cut a trapezium off it by cutting across a line parallel to the base. So if you've got 1 pair of parallel edges, but no equal angles specified, that makes it a general trapezium in England or trapezoid in the USA. Okay, now let me just go back a bit. And now, where do I put ticks on the right-hand side? These are other properties. So I tried to show you minimal sets of minimal properties that would define these shapes. Now then, are the opposite edges equal for a square? Yes or no? Yes. Think about it as I go on now. Are the opposite edges parallel? Yes. Are the opposite edges equal? Yes. Is there at least 1 pair of parallel edges? Yes, there's 2 actually, but there is at least 1. Are there 4 equal angles? Yes. Are there exactly 2 pairs of equal angles, but they're not all equal? No, because they're all equal. You can have 2 pairs of equal angles, you see, in a rhombus, okay, but they're not all equal. So that doesn't apply in the square. Now, is there at least 1 diagonal is perpendicular to the other? At least 1 diagonal is perpendicular to the other. Okay, yes, for square. Actually, they're both perpendicular to each other. So if we go on now, the opposite edges are parallel, are they? In a square, in a rectangle? Yes. Are the opposite edges equal in a rectangle? Yes. I want you to think of whether it's yes or no before I show you the tick, okay? Now, can you think of it whether in a rectangle there's at least 1 pair of parallel edges? Yes. Did you get that? Now then, for a rectangle, are there 4 equal angles? Yes. Are there exactly 2 pairs of equal angles, but not all equal? No. And also, at least 1 diagonal is perpendicular to the other. The diagonals are not perpendicular in a rectangle. And that's what distinguishes a rectangle from the special case of a square. For a rhombus, are the opposite edges equal in a rhombus? Yes, they are. The opposite edges are equal in a rhombus. Is there at least 1 pair of parallel edges? Actually, there are 2, so the answer to that is yes. Are there 4 equal angles? No. What about for a rhombus? There are 2 pairs of equal angles, but the angles are not all equal. That's where a rhombus gets its tick. Okay. So this is really subtle, but it's very. I hope it's clear. At least 1 diagonal is perpendicular to the other. Well, actually, they're both perpendicular to the other, so that gets a tick. for a rhombus. Now we're coming on to a kite. So are the opposite edges of a kite parallel? Does that get a tick? Yes or no?
No.
No. So if we go on to the next one, are the opposite, for a kite, are the opposite edges equal? No. What about at least one pair of parallel edges? No.
Oh.
What about 4 equal angles? No.
Oh.
What about exactly 2 pairs of equal angles? Don't think that's true either. And what about at least one diagonal is perpendicular to the other? Yes, that one is true for the kite. So at least one diagonal is perpendicular to the other, but none of the other properties hold for the kite. So that's our kite. Now then, if we come on to a general parallelogram, what about opposite edges are parallel? Yes, that's a parallelogram. And opposite edges are equal? Yes, for a parallelogram. What about at least one pair of parallel edges? For a parallelogram, well, it's all in the name, yes. Has it got 4 equal angles? No. But it does have 2 pairs of equal angles. Opposite angles are equal, but they're not all equal. And what about this last thing? At least one diagonal is perpendicular to the other. No, not generally. It would be true if we took a special case like square or yeah, rectangle or rhombus, which are all parallelograms, but they're special. Okay. Now then, if you go on to the isosceles trapezium, it doesn't have both pairs of opposite edges parallel, and it doesn't have both pairs of opposite edges equal, but it does have at least one pair of parallel edges. That makes it a trapezium. And to make it isosceles, it certainly doesn't have 4 equal angles, but it does have 2 pairs of equal angles. So we get a tick there, here. And at least one diagonal is perpendicular to the other. And the answer to that is no, that doesn't apply. But now, what makes for a general trapezium that doesn't have the symmetry? And that is simply that it has at least one pair of parallel edges, but it doesn't have equal angles. All the 4 angles are different.
So our learning objectives were to really embed and reinforce, so by discovery and investigation and manipulation, so that the learners really understand about quadrilaterals. They can name and classify them, identify the minimal information, which is really valuable, so they can, if they get a problem, they actually know, they can identify the shape given the minimal information in a problem, which is a common thing in the questions. And they can sketch quadrilaterals.
Yeah. And with this minimal information, I think what they're getting out of that is critical thinking. That is, you know, what's true here? What do I need to know? This minimal information. Critical thinking is one of those life skills that's really important. And which one in particular stood out for you?
Well, a lot of them, but I really liked identifying sets of similar rectangles, because I thought that got you into a lot of conversations at the 14 different rectangles there. And, you know, for elementary or primary school children, I thought it was a good introduction to rotations, and I really liked that activity, actually. Yep.
Yeah. Okay, Caroline, did you have one that stood out for you?
They were all amazing in so many different ways, but I loved using the wax paper in the kitchen to really get solid on the relationships between parallel lines and opposite corners using 2 rulers, pencil, and kitchen wax paper. And you can use that in both in primary without going into depth, and in secondary, when you really do need to work out the actual angles, you still, like in both cases, you get insight on relationships there, and it's beautiful.
Well, I'm going to pick out this card sorting with sets of cards A, B, C, D, E, F, because we're so much in that. And in general, we did some research in AIMSEC with some other with some 8 European countries. Actually, it was a lot of research about formative assessment. This is for learners to do some self-assessment, really, by sorting the cards. And that's what's so beautiful about this card sorting exercise. It is actually, if you get this done by pairs or groups of learners, they actually do some revision. They find out for themselves what they know and understand and what they don't know. That's formative assessment. They help each other to get their ideas straight, so the teacher doesn't need to explain everything. So this card sorting we recommend it as a really good way to do revision. Now, for transitions, when you come to year 7 in England and grade 8 in South Africa, and also grade 10, you want to assess. You meet these young people, these learners, and you want to be able to do some formative assessment of what they know before you move on. So when they arrive with you in grade 8 in South Africa or in grade 10, right, FET, by doing this card sorting, you can they can revise what they should have done in earlier grades, years, and they can self-assess on that. So that's why I'm picked that one out.
Now, the Aiming High Learning Packs is a web page that contains hundreds of activities, rich mathematical learning activities to help you in the classroom. You get the PDFs of the worksheet, templates with instructions. We've got videos on our YouTube channel, which is called Maths Toys. Got notes for teachers. You've got inclusion guides. So you've got the inclusion guides cover from low attainers or young, either the young or low attainers, all the way through to leaving school. And we encourage you seriously to use them. They're really not taken advantage of much. We use everything that Tony creates on here. There are learning guides that go with them. There are hundreds of activities already there on the Aiming High website, and you can search by topic, you can search by year, you can search by just searching the normal search for the name of something you want to work with. Please do use it.
And you'll get solutions to all the problems, curriculum links, diagnostic quizzes, suggestions for teaching. You'll get questions to ask to guide learning. You'll get follow-up ideas. There's a lot there. Okay, so there it is, the website. It's our AIMSEC family. It's our online forum where we've got stored lots of resources for you, and I hope you'll enjoy using it and find it. So we've got properties of parallelograms, properties of quadrilaterals, is a square a rectangle, and those are 3 different learning activities, but there's an overlap between them, as we've discovered this afternoon.